Hey guys, this is 5.2 part 1. We're going to be talking about power functions in this video. Alright, so what is a power function? It is a function that can be represented in the form f of x equals k times x to the power of p. Okay, there's nothing being added or subtracted there, it's just one term on that side, on the right hand side. Okay, and k and p are just real numbers, and k is the coefficient. So you've got some real coefficient there, and then you've got a power here, and that is a power function. All right, so it's not going to be having anything added or subtracted afterwards. That is just it. All right, so we're going to talk about some properties of power functions. If you have an even power function, so that's talking about your exponents here are even, 6, 4, 2. They're all power functions with even exponents. And then you can see them graphed over here to the right. You can see x squared, your standard parabola, and then you see x to the 4th in orange, and then x to the 6th in blue. They're all shaped like the quadratic parent function, right? They are all shaped very similarly to the parabola. Just notice, try to look at those graphs and see what actually happens as the power gets higher. Well, higher powers cause the graph to flatten near the origin. So if you look close to 0, 0, you'll see that the higher the power is, the more flat it is at the origin. The blue, that navy blue being the flattest, well, that's because it's x to the 6th. That's the highest power that we have here. And then x squared is the least flat because it's the lowest exponent that you have there. And then they become steeper. Oops. I can't write today. Steeper away from the origin. So as you move away from 0, 0, you'll see that your graph becomes more steep the larger the exponent is. So x squared is the least steep curve that you have here, while x to the power of 6 goes up very quickly, and it is the most steep you have. The higher the exponent, the more steep it's going to be as you move away from the origin. Now let's talk about symmetry. So looking at all three of those graphs, you hopefully can tell that they are symmetric about the y-axis. And that brings me back to something else. We've already talked about graphs that are symmetric about the y-axis, and we called them even, right? Well, it makes sense because now we're looking at even power functions with an even exponent, and it turns out that they are even. They are symmetric about the y-axis. So not a big surprise. Now, end behavior. So end behavior is talking about what happens to your curve or to your line as x gets really big, so approaches positive infinity, or as x gets really small, which means approaching negative infinity. So let's look at our graph and think about this. So as x approaches, that's what this arrow means, approaches. As x approaches infinity, f of x, which remember is your y value, so just your curve, is approaching what? So as x gets larger, what is happening to my curve? It's going up. It's going up, 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 up. So y, or f of x, is also approaching positive infinity. And then as x approaches negative infinity, so as we move this direction on our graph, what is happening to the curve there? Well, it's still going up, 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 up. So as x approaches negative infinity, we're also going to be going up forever, and so that's also approaching positive infinity. So this one we can write as x approaches positive or negative infinity, f of x approaches positive infinity. It doesn't matter which way I go here, left or right, my graph is approaching positive infinity. Okay, so that is end behavior. All right, what about odd power functions? So odd power functions are going to have odd exponents. Any power function with an odd exponent is an odd power function. Makes sense. And here's what they look like. You can see the graphs on the right. They are all shaped like the cubic parent function. So you see x cubed there graphed in teal. And then you see the other three all look very similar. Again, higher powers, higher or larger powers cause the graph to flatten. Still causing it to flatten closer to the origin. So you see that the most flat is that dark blue again, and that's because it's the largest exponent. That one is x to the 7th. And then the least flat near the origin is the x cubed in teal, because that's the smallest exponent you have. So the larger the exponent, the flatter it is near the origin. And then it's going to become steeper away from the origin. So as you move away from 0, 0, it's going to be more steep if it has a larger exponent. So you see x cubed, not quite as steep, although it is still very steep. But it's not as steep as x to the power of 7, which is going up much quicker. All right, symmetry. This is symmetric about the origin. And remember, we talked about symmetry about the origin with odd functions. Again, this is an odd function, so it makes sense that it's symmetric about the origin. And remember, that just means you could turn it 180 degrees, rotate that 180 degrees, and it will look exactly the same. End behavior of odd functions. So let's go as x approaches positive infinity. So as we move to the right, what is happening to the y value? The y value, or f of x, is going up, and it's going up forever. So that is approaching positive infinity. And then as we go to negative infinity, as x approaches negative infinity, the curve goes down. It goes down, 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 down. So it's going to keep going down forever. So that is approaching negative infinity. So all of these graphs are going to follow this pattern that we have here. So even ones are going to go either, both sides are going to be going up for their end behavior. So both sides are approaching positive infinity. Whereas cubic, it's going up to the right and down to the left. It's approaching positive infinity to the right and negative infinity to the left. And then both graphs, whether even or odd, you notice that they are more flat at the origin the larger the exponent is. The higher the power, the flatter the graph's going to be near the origin. And the higher the power, the steeper it's going to be as you move away from the origin. So they are all going to follow those patterns. All right, next page. That is not the next page. There it is. Okay. So let's talk a little bit more about end behavior. If the coefficient k is positive, the end behaviors described above apply to even and odd power functions. So just like we just talked about, the end behaviors are going to apply if k is positive. So the ones we just talked about apply if k is positive. But if k is negative, you know, that's going to make your graph flip across the x-axis. It's going to cause it to reflect. It's going to cause a reflection over the x-axis. So if your graph reflects, then the end behaviors are going to switch, right? They're going to become the opposite of what they were if it reflects over the x-axis. Okay, so I've got this table here for you to try to just, you know, have all of the possibilities here. If k is positive, then you've got your parabola and your cubic function, just like your standard parent functions. And with those, the end behaviors for the even are going up as x approaches positive and negative infinity. And then for odd, it's going up as x approaches positive infinity and down as x approaches negative infinity. So you have these end behaviors. But if k is less than 0, so k is negative, then it reflects over the x-axis, and now on your even power functions, it's going towards negative infinity on both sides. And then for your odd power function, as you move to the right, it's going down instead of up. And as you move to the left, it's going up instead of down. So now your end behaviors are as x approaches negative infinity, f of x approaches positive infinity. So that's saying as x goes towards big negative numbers, f of x, your y value, is going towards positive numbers. It's going up. And then opposite on the other side, as x approaches positive infinity, f of x is approaching negative infinity. It's going down. All right, so those are your end behaviors, and they're going to follow that pattern no matter what. So all you need to know in order to determine the end behavior of a graph, of a power function, is you need to know, is my coefficient positive or negative? Is it even? Is the power even or odd? And then you'll know how it's going to behave on each side. So let's look at these examples. Describe the end behavior of the function. F of x equals 3x to the power of 8. So first thing I notice, it's even. Okay, so that means either both sides are going up or both sides are going down, like a parabola. And then I notice that my constant is positive. So I know it's not reflected over the x-axis, and both sides are going to be going towards positive infinity, just like a parabola. So let's write our end behavior. As x approaches positive or negative infinity, right, because we're talking about an even function, we know both sides are going to be going up, so I can say as x approaches positive or negative. You can write that separately if you want, but both ends are going to be going the same direction. So you can also just write this one time, since both sides are going the same direction. So as x approaches positive or negative infinity, my f of x, or my y value, is going to approach positive infinity. If it helps you, you could sketch a graph, right? Because it's even and my k is positive. I know my graph is going to look something like that. So as x approaches positive infinity, f of x approaches positive infinity. Okay. Now next one. G of x equals negative x to the power of 9. So first thing I notice is that this is odd. So it's going to look like a cubic function. And then I notice that my coefficient is negative, which means it did flip over the reflect over the x-axis. It reflected over the x-axis. So here's a little sketch of what that would look like, right? It's cubic. Well, it's not cubic, it's the power of 9, but it's going to look like the cubic function reflected over the x-axis. So it's going to look something like this. Okay, so that is as x approaches positive infinity, I don't need to write a plus sign there, as x approaches infinity, f of x approaches, so as x gets larger, what's happening to your curve? It's going down. So that's going to be negative infinity. And then as x approaches negative infinity, f of x approaches, okay, so as I move to the left, as my x values get really negative, what's happening to my curve? It's going up. So that's approaching positive infinity. And that's how you describe end behaviors for graphs. And not just power functions, that's any function at all. That's how you can describe end behaviors. What's the graph doing as x gets really large or really small? All right, so that's it for part 1. We will continue these in part 2.